Section 3.1, page 1, focused on exponential functions. Our goal is going to be to take derivatives of exponential functions, but first we need to highlight some key components of an exponential function. All equations that are exponential will have the form of some coefficient and a base value or a base amount to the variable. So what you're supposed to notice is that the input variable is in the exponent. It's no longer in the base. Before we would see something like f of x equals x to the b power, and x was in the base. To review a couple key exponential formulas or laws of math, keep in mind, even though you're seeing x here, we're focused on if two equations have the same base, then we can, and they're multiplied together, we can add the exponents. If two amounts are being of the same base are being divided, we can subtract the exponents. If you have a base to an exponent and that equation is to, or expression is to an exponent, you would multiply exponents. And even if you could see it as a product of terms to an exponent, then you can keep it where each individual has the exponents, but it's still a product. The piece we really need to focus on is what is the graph of an exponential function. We'll go ahead and let A not exist right now. And I should have pointed out this key piece. A does need to exist. It can be 1. That's what it is in our equation below, but it can never be 0 because otherwise this whole thing is 0. And B is never going to be 1 because 1 to any power is just 1, so this function wouldn't really change. But we are going to focus on equations where B is always positive. But that doesn't necessarily mean that we can't have exponential growth and decay. So we know that B has got to be above 0. It's got to be positive. But what if it's a proper fraction, such as x equals 1/2? I went ahead and did the math to show you 3 points on this curve. But what you want to focus on is it's almost like this L shape, where if you were to take the limit as x goes to infinity, it basically flattens out to an asymptote of 0 on the far right. And because the graph is going to continue to grow and grow forever, the limit on the far left, when x is negative infinity, will be infinity. Whereas we have the reverse when b is greater than 1, so it's an improper fraction. We're going to see this steep spike in growth. Here's the math if you'd like to look at it, how I got 3 points to help you see the curve. But when we're looking at this curve to the far right, when x is infinity, it's going on forever and ever up to infinity. Whereas on the left of the graph, again, we've got that horizontal asymptote looking shape of 0. And one last piece that's very important when it comes to exponential functions is we're going to want to talk about e to the x power. E is referred to as the natural number found using the equation in the box. But basically, it is an irrational number, meaning the decimals go on forever without repeating, even though you may feel you're starting to see some sort of pattern. And we often approximate it with 2.71. So keep in mind, 2.71, a little bit bigger than 2, slightly less than 3. So a graph of e to the x is somewhere in between the graph of 2 to the x and 3 to the x.